I'm Rohit Kumar Singh, one of the TA for this course, Nuclear and Particle Physics. Uh, and this is the 10th live session for this course. so, uh, in this session we try to, recap some concepts and solve some sample problems for the week. So I expect that you have gone through the lectures for this week, mainly the interaction of two, electrons or fermions via the electromagnetic field represented by A mu, things like that. But I will try to recap these things a little bit, and during the solution of some problems. Okay, so let's get started. And if you have any doubt at any point, please ask. Okay, so let's have the first problem. Okay, can you see it? Hello? Are you able to see the question? Okay, thank you. Okay, so yeah, it's a simple problem of gauge transformation. We discussed it in the last lecture also. So, here gauge transformation is given. So you might have seen this type of transformation earlier. So the force potential A mu is transformed like this, where lambda is a constant function of space and time. And so under these gauge potentials, under these gauge transformation of this potential for potential, we have to find out what happens to the field strength tensor F mu nu. Okay, so F mu nu you are familiar with. Okay, now there are 4 options given, and we have to find out what happens when we change A mu like this to the F mu nu. Okay, so any guesses? Can anyone guess which is the correct option? So one thing you will notice is that all of these options are, so for example, this one and this one, so this one is not, obviously. So this and this, all of this involves the field strength tensor. Okay, so we have to first see what happens to the field strength tensor under this transformation. So let's write F prime, which is given as it's given in the problem also, A prime and del mu of A prime mu. Okay, and let's replace the A prime using this expression. Okay, so here, because the index is nu, so we will replace everywhere nu, and here the index is mu, so we'll write mu. Okay, this is fine. Now let's see what happens. So this is del mu A nu minus del mu del mu lambda minus del mu a mu minus plus del mu del mu lambda. Okay. Now let's take these two together. Okay, and this are essentially the same thing, because the only difference is the order of differentiation, just the interchange of mu and nu indices. So it doesn't matter, because you know that if you have a del mu, it is same as del mu. Okay, the order doesn't matter, right? So that's why this and this get cancelled, and you're left with this, which is just f mu. Okay, so we found out that option 1 is correct. Okay, the field strength tensor is invariant under the given gauge transformation. Now what else can be correct out of these options? Can this be a correct option? Anyone? So option 2 cannot be correct. So yeah, so let's check. Okay, so let's write del mu a nu prime f mu f prime mu. Now we already saw this is equal to f mu nu, right? So we can just write it like this. Okay, now let's change this. So so a mu a prime is what? A prime is so let's take a bigger bracket. A mu minus del mu lambda. Okay, I've written the covariant form, because here we have a newly written covariant form. Okay, and then if mu is there, so you see that there is no way to make it equal to this, right? I mean, you cannot make it equal to right, because this term is there, this term uh, del mu lambda, it is always there, right? You cannot cancel it with something else. So this option cannot be true. Similarly, you can check that this option is also not true. Okay, so do you want me to check this one? Let's check it. It's simple. So let's check this option C. So this is a mu minus del mu lambda, and then a mu minus del mu lambda. So sorry. So you get so we'll just multiply both. So you get a mu a nu, and then you get cross terms like a mu del mu lambda and del mu lambda a mu, and then del mu lambda, right? Now so this is obviously not equal to a mu, right? Because you have these non-zero terms, and you cannot arbitrarily make them zero. So this is also not correct option. Now the fourth option is trivial, right? Because we know that f prime is invariant, so uh, the dot product of two field strength tensors should also be invariant under this gauge transformation. So this is trivial. This is always correct. So yeah, option 1 and option 4 both are correct. Okay, and these two are not. Is it okay? So what I'm saying is, since f prime mu nu is equal to f mu nu, f mu nu, f mu nu, so if you take dot product, will also be equal to f mu nu prime, right? So this is what the last option is. Okay, I hope this is clear. Any question? Okay, thank you. So then let's move to the next problem. Now, so here the question is, along with the given statements of question 1, consider the three Lagrangians given as follows. And then we have to consider another transformation for psi, and then this is the gauge transformation for potential, and under these gauge transformation we have to check these options. Now you know these psi, right? This is the fermionic wave function whose solution can be found using the Dirac equation. But we don't need to, know the solution here. We have just been given a gauge transformation of this wave function like this. Okay. So if psi transforms like this, then the Hermitian conjugate will transform like this, right? So here here the negative sign in the exponential will be now positive, and this is the transformation. So this you have to find out yourself in this problem. This is not given, but this will be true, right? If you take Hermitian conjugate, minus I will become plus I, right? I go to minus I when we take the Hermitian conjugate. And we again have this gauge transformation of the potential like this. Okay, so this is given, and we have to find out what happened to these Lagrangian. So let's first check the let's first check the first option. Okay, so L1 plus L2 plus L3, which is I psi prime psi bar del mu psi plus E psi bar gamma mu psi dot A mu. Okay, so this is L1 plus L2, and L3 we have the scalar product of f mu. So we already saw that this is always invariant, right? We just saw in our first problem that this is invariant under gauge transformation, right? So L3 is invariant, it is trivial, right? Only the minus 1 by 4 constant is an extra, which is anyway invariant because it is just a constant, right? So we don't have to worry about the L3, we just have to check whether L1 and L2 are invariant under this transformation. Okay, so let's check. So then let's write L1 prime plus L2 prime, and this will be I psi bar prime gamma mu del mu psi bar psi prime plus E psi bar prime gamma mu psi prime A mu prime. Okay, are you following? Okay, so now we will substitute the values of psi prime bar and A mu bar, okay, in this one, and we'll see what happens. So let's do that. So psi bar prime given here, okay, exponential I E lambda psi prime gamma mu and del mu of psi prime. That means we have to differentiate this whatever we have under the in the bracket. Okay, we will do that in the next step. Let's just write everything here first, and then again psi bar prime is E lambda psi bar gamma mu, and then psi prime is E minus I lambda psi, and A mu prime is A mu minus del mu lambda. Okay, this is multiplied the work. Okay, now let's differentiate this in this step. Okay, so here we have I e to the power I lambda psi prime gamma mu, and here are two functions. Okay, and you know that lambda is also a function of x, so we'll have to follow the chain rule of differentiation. So first we will differentiate this keeping this constant, and then this differentiate this keeping this constant. Okay, you know how to differentiate. So del by del x of AB is equal to del of del x of A, right? B is constant, and then A del B of del x. This you know, right? Similarly we will do that. So here A is exponential function and B is a psi function. Okay, so you know that differentiating an exponential gives out the same function, and by the chain rule of differentiation we will get del mu lambda, right? Because lambda is also a function of x. If lambda would have been a constant, then this will be I mean it will be essentially 0. It would have been essentially 0, but since lambda is a function of x, so and then we have psi plus, here we will differentiate psi keeping the exponential constant. Okay, so this is what you get by differentiating this, whatever we have in the big bracket. And for the second part, you can already see here this and this multiplied will give you 1, right? Because it is positive and this is negative, so it will just cancels and give you 1. So what remains here is E psi bar gamma mu psi, and in the bracket we have A mu del mu lambda. Okay, now you see everything is coming together. So now let's multiply this into whatever we have in the bracket. So first you see that this multiplied with exponential will give you again 1. So we will have psi bar gamma mu del mu psi. Okay, and 1 psi here. Is it fine? Please let me know if you are not able to follow, then I will do more steps. And then this multiplied with this second term will give you essentially so here again the exponentials will cancel out, and then you are left with I psi bar gamma mu del psi. Okay, and now the second part we have we will just multiply it into the bracket A mu, okay, minus E psi bar gamma mu psi del mu lambda. Right, now you see this cancel out with this, and you are left with what you had in the beginning, right? So this is your so this is your L1 and this is your L2, right? So what we found is L1 and L2 is invariant under the gauge transformation, and we also know L3 is invariant, right? So which are the options are correct? So first is correct, third is correct, and fourth is trivial. Okay, is it okay? Were you able to follow all the steps, or you had some problem in some steps? Please let me know. This is very simple, right? You have to just work it out. Should I move on? Hello? Okay, yeah. Just to make sure, yeah. Okay, thank you. Then let's go to the next problem. Okay, so yeah, this one is little tricky. I mean, I don't know if you have gone through the lectures or not, but so in the lectures there is a discussion of interaction between two electrons. Okay, so two fermionic particles, and here the question says you have a charged scalar particle phi x. Okay, so this is not fermion. This is the solution which you get from say from the solution of Klein-Gordon equation. Okay, so it's a charged scalar particle. It is charged, but it's a scalar particle, not a vector fermion, and it interacts with so this one interacts with a electron represented by psi. Okay, and the corresponding current is given. So this is the charge. This is the current given for the scalar particle. This is the charge density. First, so we know that the first component is the charge density rho, right? So this is just the charge density, and the second is the uh, current density. G. Okay. So and this is the G, current density. And similarly for the electron, the corresponding current is given. So this is the four current, and you have seen this uh, in the Dirac equation lectures. So for electron, the current is just this, okay, and it's, if you want to write it in terms of zeroth and I mean in terms of temporal and spatial component, you can write it like this. So this is, so for spatial part you have gamma 0, okay, and in the temporal part you have spatial part, this is the temporal part, which is charge density, and here you have gamma I, basically where I goes from 1 to 3. So this is the right. And this one you can solve a little bit. So we know that psi bar is nothing but the Hermitian conjugate, Hermitian conjugate into gamma 0, right? This is the expression. So so the rho, so rho is nothing but this quantity, okay, and J is always this for electron, okay. So yeah, these things you might have seen in the lectures, right? And for a scalar field we have these rho and J. Now how do we write the transition amplitude for their interaction? So any idea? Okay, so yeah, let's try something. So you know the Dirac equation, right? Gamma mu p mu minus m psi is equal to 0. So this is the Dirac equation for a free electron or free fermion without any interaction. Now suppose this fermion, which is free, is now experiencing some kind of force. It's in some kind of field, okay. Say, so let's take the electromagnetic field, and it is represented by the electromagnetic field is represented by the four potential A mu, right? So in presence of A mu, what happens is this momenta P mu, it changes like this, okay, and this Q is the charge of the electron. which we know is minus E, negative charge, and magnitude is the electron. I mean, uh, this is the quanta of charge, right? The electron carries. So then this equation becomes something like this. Okay. So in presence of an electromagnetic field, the Dirac equation uh, changes like this. So now this is a Dirac equation for a fermion which is experiencing electromagnetic field represented by a mu. Okay. Now again, I mean this. Okay, this is an equation, but how do we find the solution for this equation? You cannot just write an arbitrary solution, right? So let's let's try to get a simple form of this Dirac equation. Okay, and to do that, let's break the components for this. Sorry, this should be gamma. Okay, into spatial and temporal parts. So let's write gamma 0. Sorry. Let's first take them out of the bracket. So psi minus m psi is equal to 0. Okay. And then let's break this into a spatial and temporal part. So this is gamma 0 p0 psi plus not plus, minus gamma dot p. Okay, and we can take this inside psi. Okay, and we are left with the second term. So why we are doing this will be clear in a moment. Okay, and then let's multiply it with gamma 0. Okay, so and we know that gamma 0 square is 1, right? We discussed this in the last lecture. This can be easily derived using the anti-commutation relation of gamma mu. Okay, you know that gamma nu anti-commutes. So you can just put 0 0 and you will find it's 1. Okay. So then here gamma 0 will give 1. So we are left with P naught, right? Psi minus gamma 0 gamma dot P minus m gamma 0 psi. Sorry. Here is one psi, here is one psi. Okay, fine. And then here we have the same thing. Okay. Now we know that the zeroth component is just the energy E by C, and we can take C equal to 1. So it is just E psi, right? And let's take it to the different other side of the equation. So let's take all of this on the right hand side. So we will get gamma 0 gamma dot P psi plus m. Yeah. yeah, m is yeah, m should come with psi plus out minus this quantity. Okay, now you have this equation, right? And let's compare it to the Schrodinger equation. So we know that Schrodinger equation is given by this expression, right? Now comparing this and uh, this and this, we see that this is equal to the H naught and this is the potential V, right? So for example, here we have H naught and here we have V, and so we have found out a potential. So this is a potential corresponding to an electron interacting with EM field represented by AM. Okay. Now, since we have found a potential, uh, it is a, I mean, now it is trivial to find a solution for AM. So, so, so the definition of transition amplitude TFI is given by, so suppose you have a incoming electron, okay, given by psi function psi in, and it interacts with some potential a mu and goes out the fine psi f after interaction, and this is represented by the current J mu, okay, this electron. So the transition amplitude for this process it is given by this, right? So you have the incoming and then the potential. So this is simply from quantum mechanical picture integrated over all the space. There is a constant factor of one side. Okay. Now we know the potential which is responsible for this interaction. So let's insert that. So minus minus it is now plus E psi bar gamma mu psi a mu d4x. Okay. So what we have done here is we have simply written this as, so this we already know, so I have just replaced this with psi bar, I mean, okay. So this is the transition amplitude now, and now you remember this one, right? So what is this? So we can write it like this, right? Because you remember I wrote here the current, the 4 vector current J mu is given by minus E psi bar gamma mu psi, right? So you have an expression for transition amplitude in terms of the current corresponding to the electron and the surrounding electromagnetic field, I mean represented by A mu, Okay. Now this is now interesting, and this a mu can be found out as a function of uh, another current produced by the source of, I mean, source electron. So for example, uh, you have a electron 1 e1, okay, which is, as I mentioned, which is represented by wave function psi in, and it is interacting with an electromagnetic field a mu, and out goes the final wave function f psi f. Now this a mu is, it is getting produced by another electron, okay, and its current density is J1 mu, and this electron 2 has current density of J2, given as J2 mu, okay. So in this picture, uh, you can write the Maxwell equation, which is, right. So this is the source current J2 responsible for the this a nu the field, okay. And if you consider plane wave solution, you can take you can write a mu as, you can solve a mu as this, where q is the momentum transfer. So this is p1 minus p2, simply that momentum transfer, okay. And so now you can write the transition amplitude as minus I j1 minus 1 by q square j2. Okay, or you can take the indices up. So j1 mu g mu nu by q square j2 mu d4x. Okay, so this is the transition amplitude for interaction of two electrons. Now let's understand this. Here you have current J1 and a current J2. Okay, J1 is the our electron the current corresponding to electron E1, and J2 is the current corresponding to electron E2. Okay, so this is a very general equation. Now in our problem, what we have a scalar particle, a scalar particle given by the wave function phi, and this is now interacting with an electron field, okay, via the electromagnetic field produced by this electron. So this equation will not change anything. You have to, instead of the J1 for an electron, you will just use the J1 for the scalar field, okay. So if you can see in the option, you have this thing, right. So here the J1 is the J of current of the scalar field, and it is the current of the electron incoming, and this is this will give you the transition amplitude corresponding to their interaction, okay. So this one is the correct option. So in general, if you have an electron and you have any other particle, whether it's scalar particle or another electron, another fermion, you will just change the expression for in this transition amplitude. You will just change the expression for the current density. That's all. This will give you the transition amplitude. Okay. Okay, so now let's take the fourth problem. Here we have a scattering process A plus C going to B plus D, and the four momenta for all of them, not all of them, for the three of them is given. So this is given. So four momenta of P of A is given like this. For C, it is same with a negative sign, and for B we have in terms of sine and cos theta. Okay, now so what is happening here is A and C are incoming, they are interacting, okay, here, and out goes B and D. So A and C are incoming and B and D are outgoing. Okay, and now the question is we have to find the four moment of D. Okay, so this is simple, right? Because I mean the momentum should be conjugate. The four momentum should be equal. So EA plus EC should be equal to EB plus BD, right? So let's write it. So PA plus PC. So let's add these component wise. You will get this 0 0 0, and PB you have theta 0 and cos theta, and then you have P0, P1, P2, P3. So now you can just looking at these formula, you can just see that so yeah, let's equate the component wise. So under root s should be equal to under root s by 2 plus P0. So P0 should be equal to under root s by 2. Okay, and similarly you can see that P1 should be equal to minus sine theta, P2 is should be equal to 0, and P3 should be equal to minus cos theta, right? So this means that yeah, option A is correct. Okay, this is very simple. Now let's go to the last problem today. Here we have to find the mass of the particle A given in the question 4. So what was EA here? So EA was 0 0 under root s by 2. Okay, so this means E is given and P square, and so yeah, P 3 moments. So basically you can take this to be Pz, but you can write it like this, and we know that from Einstein relation E square is equal to E square plus M square, right? So that means S by 4 should be equal to S by 4 plus M square, and we see there here is M is 0. So this is a massless particle because here E is just equal to Pj, E square equal to P square. So the mass is 0 here. Okay, so this is the last problem for today. See you next time. Thanks.